Okay, so here is the example. Here you see the output vector maybe like this. Okay, so in general, the output of the network does not sum to 1. Okay, so we usually do some normalization again over here. So here is a terminology called softmax. Okay, so the softmax you can treat such a layer as the output layer. Then this layer will do the normalization. Okay, so here you see, so the activation function, your C1, you produce Y1, Y2, and Y3. But their summation, their sum is not 1, right? Usually it will not be 1. Okay, so how to do it? Okay, so here, in this case, in this example, you see the output here is 20, and this one is 2.7, and this one is 0.05. Okay, so their summation is not 1. Yeah, but we just summarize all of them together. You can see the summary will be 22.75, right? And you can use it as the denominator here. And then the numerator is their original value. Okay, so we produce. This is just a fraction here, and the summarization will be 1. So such a technique is called a softmax. And so sometimes we will use the softmax. So if you think such a normalization is very important, so you can apply this technique here. Okay, depending on your choice. So for example, in this case, if we want to interpret such a result as a probability or constant, so it would be good if you transform it like this. Okay, rather than use it. Okay, so we add one more layer called the softmax layer. Okay, over here, so now you produce a vector, a 10-dimensional vector here. Okay, so the result looks good, because you can see here this neuron has the highest value, right? Corresponds to the answer 2. So it means for this image, we think is input, the answer is 2. Okay, so it looks a very good result. So that's how to let the neuron to achieve this. Okay, so we have to do the training to let the neural net learn how to build up a very accurate model. So here we prepare training data with images actually are the vectors in this data set. Actually just prepare the data set. They are all the raw data. Okay, so raw data and their labels. So for example, this image, I will give you, in this data set, I will give you for each image is a 256 dimensional vector, and with their label, for example, it's 5, 0, 4, like this. Okay, so here is our training data. You see, it's a supervised level. Okay, and let me ask you a question. So what's the difference between supervised and unsupervised learning. Okay, do you know?对啊，对，我们的差别是什么？有个正点，然后这个回答没有很到位，再更精准一点，说得更精准一点。The explanation is not very precise. If nobody knows the definition of a supervised and unsupervised learning.你再说一句。那这是这就是学习，那这类就是呢？不够精确，这样讲不够精确。I hope you can give me a very precise explanation about it.你们之前都没有学过的训练或者培养班都没有。Okay, so okay, I can accept the last two answers. Okay, I can accept. Yeah, basically the supervised learning will use their label data to guide the learning, and for unsupervised, we will not use the label data. Maybe we have this data, but we will use it to test if it is correct or not. But learning phase, we will not use the label information and just let the data, use the raw data to learn some relation by themselves. We just define a metric to let them learn by themselves without using the label information. OK， 好，这个问题非常基本了，我希望上课的人都会知道。我本讲如果都没人知道，我自然课就不用上，大家去找答案，知道答案就再回来上课，不然我这样上去没有意义啊！你们都不知道什么叫supervisor，不知道什么叫supervisor，这样子我上这课还有意思吗？最基础的都知道 ，because you don't have the background knowledge, so I think I don't need to spend the time to continue the code. Because you don't know this background, so I will just stop and let you to find the answer. And until everybody know the answer, then we can continue our code. I think that your background is really very poor. Almost nobody can. Most people cannot give me a very good answer for such a very simple definition. I'm very sad. So it's your level, so poor. I don't think that such a level should be for master students. 你们这样程度太差了，连这种答案都做不出来的话。这程度非常非常差，我今天根本就不需要上课，再上下去你们听不懂，你们根本也没在听嘛。因为我讲了半天，你到底听进去什么东西？你们之后再回去再去练习嘛，再去看相关的书嘛。你们讲这门课就是好好赚学生，这些功课你们到底开始做了吗？你们新闻报告开始写，开始准备了吗？你们那个公布图案开始在做了吗？系统开始安装了吗？我说过有一个fail掉，这门课就是当掉了。而且我不会给你重交的机会，重报告的机会都没有，我没有时间。上我这个课里面这些基础知识不知道你来上，我们好歹上了一阵不是吗？难道我都没有教你什么叫supervisor能力？没有吗？如果没有，那好吧，那至少我现在知道。不过我至少知道一件事情，但是你们程度这样很差。你们这种上了大学4年连这种基本知识都不知道，你们知道马逊的对他妈以前都很红的东西啊，你们大学都不修这些课，那不修这些课，那来修我这门课干嘛？连基础都不会，你怎么会进阶的？你不要以为是坐在上就坐在这边，静静的坐着听我讲。你就有这样就可以拿到学分？你真的有学到东西吗？你们自己要好好加油啊！这样的程度是不行的。那想想看，你们就只来混学分吗？就只要拿到5分题，你这样出去工作有用吗？如果你觉得这门课对你工作没有帮助，你干嘛来修？那既然来修就好好修，该会的东西就要学会，不要连这种最基础的都不知道。OK， 好，这一段我会试着剪掉消音啊。好，我们继续来。Okay, so here we will define the code. I mean, you see the ideal answer should be like this. But our system output is here. You see, your system output is very different from your ideal result. So there's an error. We also treat it as also call it a cost. It's a cost or an error between your system solution and the ground truth. Okay, so we can based on this. Here we have the cost. Okay, you see your ground truth and your output here. And we can define the cost function between them. Okay, so how? So there are basically two widely used measures. One is you just use the Euclidean distance. So you see there are two vectors. You just compute the Euclidean distance. So it's very simple, right? The other is we use the closed entropy. So closed entropy is also very simple. And also a very simple equation. It's very good for if your output is you treat them as a probability. So you can use the closed entropy. For example, like this here. You can use like this P1. So P1, okay. So P1 means 0.2, and the Q1 is 0.2. Okay, so summarize. From 1 to 10. Okay, so you can write this P1 log Q1 plus P2 log Q2. Here you write 1. Okay, so in this case, you see here 0.2 over there. And the ground truth is this. And then for the next neuron, okay, thank you. So actually you can see all these are actually 0. And just keep okay. So for this one we can divide and okay, I should not use this because log 1 is 0, it's not good. So I should change it. Okay, so it should be like this. So it's my fault. Actually, all these are 0, and here we have the final only so it's called the closed entropy. Yeah, closed entropy. So I will tell you very similar. You see in that way we teach you. We call it the decision tree. We use the information gain, right? Information gain especially use the entropy. So it's very similar. A very similar case. So actually the entropies is higher, means the two vectors are very different. The lower the better. So the best idea is also the best case will be 0 here, means they are the same, identical. The probability distribution are the same. So if your system solution and your ground truth ends are the same, the cross entropy will be 0. Means they have no difference. So in the same case for Euclidean distance, so if the distance is 0, means the two vectors they have no difference. They have the same vector. So that the Euclidean distance is 0. Okay, any problem? data. Here then we can, for this data, you see, is we treated the first one. This first one data is a 256 dimensional data here, and the slower neural network without 10 dimensional output, 10 dimensional vector as the output here, and here is the ground truth. So we can compute the cost C1 for the first training data, and this is the cost for the second training data. So we just summarize all them together with the total cost. So we hope the total cost can be minimized, can be very, very small. So how to do it? I want to minimize the cost function, this cost. So the simplest way is this one. Nobody knows? Do you learn the calculus? 你微积分没学过吗？如果我要求这个函数的最小值，要怎么做？要求这个函数的积。Just apply the calculus, right? It's the simplest way. So make its first derivation to be 0. Then you can find its minimum value. Okay? So I hope everyone should have the background. Otherwise, you should come back to the undergraduate course first. 我希望大家都有点程度，不然你们应该去重修大学部的课。那我讲这些课，这些术语你们都不懂，那我上这些课有什么意思？那你们都不问了，虽然你们问这种基础题目我很生气，但是总比你问，我觉得总是我问还比较好。OK， 看你们都没反应，我就觉得大家不会，大家都不知道，这么基本的东西都不知道。Okay, so here we apply an approach called gradient descent. The gradient descent is not we can make we say we can use the calculus to find the first derivation. But actually, in most cases, you can find that you cannot always find the arrow function derivation because sometimes the function is very complicated. So you cannot always find the first derivation by using calculus. So in practice, it's not very easy. So we introduce another technique. It's called gradient descent. Gradient descent uses the knowledge. Okay, so we use the knowledge of use the knowledge of the calculus derivation difference here. Suppose this is head map. Head means the value of this cost. You can see here is the lowest cost over here, and each circle means you can see the arrow is getting larger, right? For here, this line means in this line, all points at this line, their cost is 1.5. And then will become higher. Here, you see, it means all points in this line, their cost is 6.96. This was the head map. Yeah, so suppose here we have two parameters in the network, W1 and W2. So each time we just adjust one level. You just pick one hidden layer. When you are going to adjust the neural net, okay, so you have to start it from here. Start it from here. From your output to correct the weight matrix here. Then after you adjust this, then next you then adjust this one to adjust the weight matrix here. We call this special process back propagation. You see, when we feed all input data here, we call it a feed forward, right? To generate the output. When we want to minimize the error, to tune the network, then we will use the back propagation from here, then here, and here, to back propagate the error to each hidden layer to adjust their weight matrix. Okay, so we call the process as a back propagation. And here, so suppose we in this error we have only two parameters, W1 and W2, and L. Okay, so here we can suppose we can draw a head map to just show its code. Okay, so here we pick a starting point over here. It's randomly select. Like yeah, you know, because it's the first time your weight matrix is randomly generated. It's just random. Okay, so you just random select for example this one. Okay, now this looks like you have a bad luck because it's not very looks like it's not very good. The lowest cost is here. So you have to climb down the mountain. You can think it's actually like a ball, and now you are in the border of the ball. You have to reach the bottom, so you have to climb. You have to climb along the mountain to reach the lowest point. Here we have the lowest arrow over there. So now you are here. So you have to climb down the mountain. Okay, suppose here you find that this one is at the steepest it's very, you can quickly reach the low position. So you can choose this position. This position actually is we call it a gradient. And the gradient is actually the first derivation of your function. Okay, so you just apply this. Okay, so we find here this direction is the fastest way to reach the lowest point. So just go here, lowest direction, and to here. So before your parameter is here, okay, now you reach this point, and now you are getting closer to your lowest position, right? So you will put it, and next time you will go to another direction until you go to until you reach the lowest position. Okay, so the process here we randomly pick the starting point of theta 0. It's a random initialization here. Then we compute its negative gradient at this point. Okay, we find this direction is here. It's called, this symbol means it's a gradient. And the gradient is actually the first derivation at this point. And then you can update your parameter based on this function. So actually, the gradient descent actually like this. See, your next parameter configuration will be like this. So you see your initial parameter here minus your learning rate, eta. It's not there, okay? It's eta. Eta is a Greek alphabet. We call it the learning rate. Okay, and this one is your gradient. The gradient is actually the first derivation at this point. Then use this function to update. You will get the theta 1. Theta 1 is your next parameter configuration. Then you use this to do the training again. You will obtain the next. Okay. If you want to get the next parameter, then you use the theta 1 and with the same equation. Okay, again is the gradient. You don't need to compute it again because you have calculated it. And this is just identical for every neural network. So you don't need to calculate it again. You just calculate it, and every time you can use this gradient and to update your parameter. Okay, here we show a process like this. So eventually we will reach a minimum like this to theta 1, to theta 2, and then to theta 3. And finally, after several iterations, we will reach the minimum point. Okay, so it's based, I think, just to visualize the gradient descent, the process. Okay, I didn't talk too much detail. So, for example, I didn't talk how to derive the first derivation of the function. Here I didn't mention, but you should have the concept here, the basic concept of the gradient descent. Yeah, remember we use the gradient descent, this method, to minimize the error, to adjust. Let me say it again. We use the gradient to adjust the parameter. Here the parameter means the weight matrix. We use this to adjust the weight matrix and use the back propagation process to update each hidden layer. Okay, any problems? Well, but you have to know, use the gradient descent cannot find the global minimum. You see, it's a very ugly data distribution like this. So, can you see, do you know where is the global minimum? No, it's very difficult to find, even if just a three-dimensional data, right? But you know, actually in practice we usually process the more than 100 dimensional data, right? So it's very complicated. And even for the three-dimensional data, you can see there are so many local minima. So the gradient descent is very easy to trap into the local minima and never get out from the local minima. So it will have no chance to find the global minima. Okay, so it's the problem of the gradient descent. But I think actually today nobody cares about it because actually nobody knows where is the global minima, and we don't want to hope, we don't want to spend all of our life to find the global minima. We just want to find an approximate and acceptable solution. It's okay we just need to spend maybe several minutes to find some answer that looks good, like search engine. But we don't want to find all of our life to find the best answer. Not because the data, your data set is too huge. Okay, so I think nobody care about is this a global solution? No, we just find a local solution, and it's very close to the correct. If it's very close in the 10 out of 10, actually nobody knows it's close to the best solution. Nobody knows, but it can achieve. It looks like works very well, so nobody care about it anymore. I mean, nobody cares if it's really the best answer. No, nobody cares. We just think it's a work not bad. So local minima is acceptable because we just spend a very short time to find an acceptable answer. So here we just say, you can see there will be very many different minima. So you will have a different result. So that's why we want to run several times. Because each time you just random initialize the network. Or for example, for Chih-Yi, you just randomize your initial seed. So each time you will find different results. So the best way is to run it several times. And slowly you find the minimum error and repeat it as your final model. Okay, so neural network has a similar problem. I would recommend you to run it several times to find the base model. Okay, so besides the local minima, you will also here is the cost function. You see, here we call it actually the local minima. Why? Because there is a lower over here. If you are unfortunately your initial seed here, so you will be slow the gradient descent. You will towards this direction here. But you see here is a plateau, very smooth over there, right? So your momentum, your gradient, applying the gradient descent, your momentum will get very slow. Maybe you will stop here because you find here your derivation, first derivation, almost zero. Yeah, because here is very flat. 这里非常平的，你的这样微分的话是吧？就零嘛，一些微分那个地方就零，你就是跑不动了，你就是不会修正，所以这是一个它可能停在这个地方。Maybe he will start here because his first derivation here will be zero. It's because here is very flat. So maybe you will start here or you will start in the local minimum because here is the lowest. By considering his neighborhood, the lowest, so he wants to move again. But actually, you should jump outside here to reach its global minimum. Okay, so here's the problem like this. So in this world, we can try to we add the momentum here to remedy this phenomenon. Okay, so like this. Okay, the idea is actually very simple. So here, from here you see you will have you are on a very high position here. So at this time you will look toward this direction. Here this is your gradient and this is your momentum. And when you then go to here, you can see your momentum is very strong. Why? Although your gradient is very small here because it's becoming flatter. But your momentum is strong. Why? Because you are just slide down from a very high position, right? So your momentum is very high. 因为你刚从一个很高的地方掉下来，你分量是很大的，对不对？这就是把物理学考虑进去，非常上physical principle. You see, you just drop from a very high position, so your momentum will be very strong. So just keep the momentum, add with the gradient. Then you will continue north. Okay? Here, unfortunately, you see you trap. Maybe you will trap here, but you still have the momentum. So you can use the momentum. Maybe you can have a trend to continue to climb a mountain. Okay? So maybe you can have a trend over here, and then over the mountain, over the hill, to reach the global minimum. So add the momentum, you have the more chance to find the global minimum. Okay, the idea is like this. So you can treat it as advance the gradient itself. Just add the turn momentum over here. Okay, the idea is like this, and the equation is very simple. So here is here we don't show here, but the idea, I think you know idea is okay. It's enough. Okay? Any problem? 有没有问题 ？Any problems for you? This is all right. Yeah, it's real like because we will summarize maybe we'll go back. Unfortunately, still go back. Yeah, but it has chance to cross over the field. Yeah. It gives a chance without the momentum, you will just start here and you will move it further.